Welcome back to the second section in chapter 2, where we will focus on elimination matrices and inverses, inverse matrices, I guess just to be a little bit more specific. The way that I, going through the textbook, thought about breaking this section up is to essentially put it into 3 videos. The first one, we're primarily going to focus on elimination matrix EIJ, and how we determine that, some of the more nuanced pieces of it. We saw it in the last section, 2.1, and how we can use elementary matrices to represent elementary row operations using stuff like how we solve using elimination for systems, in particular systems that get outside of dimension 2, so dimension 3, 4, 5, because the process can be used for any higher dimension versus if, from Algebra 2 and Algebra 1 classes, if you have a system of 2 equations, 2 unknowns that are linear, we can solve that by hand. You don't necessarily need a matrix for that. We will primarily focus here in looking at a 3x3. Now, as we continue to work through these elimination matrices basics, and we'll solve a problem that Dr. Strong kind of mentions as the equations 10, 11, and 12. We're going to kind of look at that as an example in this video. We're going to kind of uncover this idea of undoing a matrix, moving a matrix to the other side, which we've already seen in the form of AX is equal to B. If I want to solve for X, then what if we undid A? Well, undoing when it comes to matrices and functions is this idea of an inverse. And this section is when we'll actually get in and formally define what inverse matrices are, some special notes with inverse matrices. We'll primarily focus on that in the second video, and then in the third video we'll apply this idea of inverse matrices to this idea of elementary matrices and how we can use it to help set up a very important kind of factorization for A, which is a lower triangular matrix times an upper triangular matrix. So even by the end of this video, my hope is you'll see where this L comes from, and then by the end of this section, you should be able to then find L using everything that we've talked about. So that's a kind of an overview of all the big ideas. Let's start with this idea of the elimination matrix IJ. To paraphrase, you can see the direct language in the textbook. When I'm multiplying a matrix by EIJ, the idea is to multiply L, IJ, this is where, to row, I realize my wording is really bad, to row I, and subtract from that row J. So what we're doing with the elimination matrix IJ is we are multiplying some row in our matrix and augmented matrix, etc. Row I, we want to subtract from that row J, and I believe I actually have this backwards. So let me update that. That's where I also kind of screwed up. So this would be row J, and then this would be row I. Because the idea is we want to replace this row I by multiplying the above row, something higher. And so just to rectify my mistake, let's say we had a matrix A, and this is the one that we'll use throughout this video in particular. Let's say that A is 3, 1, 0, just kind of reading across the rows. The second row is -3, 1, 1. The final is 6, 8, 4. If we're looking at this matrix and following a similar process to what we did in 2.1, I want to identify my first pivot in this first row, and then I want to zero out every entry below it. And we zero out every entry below it by multiplying A by some elementary row matrix, or elementary elimination matrix, elementary row operation. And the first number that I want to get rid of is the entry 1, 2. So, or sorry, 2, 1. It's been a great day when everybody gets sick, including myself. So I apologize for the fog brain. We want to use E21. And what this is going to eliminate is the entry, second row, first column. And it's why when I was writing out this piece, why my mistake was there, because we're ultimately going to multiply this first row, which would be J, by some constant and then subtract it from this row, replacing this row, which is I, the second row. And so when I'm looking at this, because we're going through, the first row stays the same, so 1, 0, 0. To eliminate this, you can look at it just in terms of pure addition, but in terms of a standard, we're always going to think about it in terms of subtraction when I'm doing my elimination. So that way, when I'm inversing, we can think about it in terms of addition. So even when we're looking at this, and I'm saying, okay, well, I'm just going to add these two rows together, because that's what's going to ultimately cancel those two things out. So 1, 1, 0, 0, 0, 1 keeps the third row the same. The way that I want to think about it is -3 minus -1 times 3. So the double negatives essentially cancel each other out. So my Lij is essentially -1 when I'm looking at that entry. And this is something that's going to pop up later. You'll notice the cursive L, and then what I had up earlier, A being L times U. So that's where this notation is going to come back. Now, a lot of the ideas, again, in terms of what you see at this beginning is almost kind of recapping what we did in the previous lesson. We see that, okay, well, if I multiply accordingly, again, the idea is that I want to get A into an upper triangular matrix. We would have E21 times A. First row stays the same. Second row, -3 plus 3, 1 plus 1, 1 plus 0. Third row stays the same, so 6, 8, 4. So now we want to zero out the third row. To zero out the third row, we're going to multiply this matrix by a new elimination, so not E21 anymore, but now E31. Because again, we're eliminating the third row, first column. And in order to do that, notice how I would multiply the first row by 2, or -2, or really by 2, and then I subtract for it to cancel out. So my L in that case would be -2, or +2, excuse me. But what I actually put into my elimination matrix is -2. So again, just kind of notice that difference in what we had up earlier, that L31 is actually +2 when we get into finding L a little bit later. But E31 is here. So if I do the multiplication now, and now I'm multiplying this matrix by E31, first row stays the same, second row stays the same, but now I'm doing 6 minus 2 times 3, so that's 0. Again, that's by design. And now I'm going to do 8 minus 2 times 1, so that's going to be 6. And then 4 minus 2 times 0, which is just 4. So I have my first pivot with zeros underneath. We move on to the next diagonal. Non-zero, it's 2, so that's my next pivot. And now we want to zero out this 0, 6, 4. Now, when we do this one thing to highlight is that my elimination matrix that we're multiplying by, so E32 this time, so third row, second column, is going to be combining rows that were not in the original matrix A. Right, this matrix here has a second row of 0, 2, 1, and we're combining that with 0, 6, 4. 0, 2, 1 is not the original matrix, or the second row in matrix A. So when we're looking at the combinations a little bit later, you're going to notice that those L's that we're talking about are going to fill in, but this next entry is going to be a combination of those because there's more things happening to zero this entry out. To better see that, what I'm going to multiply this one by is 1, 0, 0, 0, 1, 0, because we want the second row to stay the same. But here, I'm going to multiply the second row by 3 and subtract that, so ultimately -3, and then add that with the third row. So I get 6 times -6, which is 0, 4 times -3, which is 1, and we have our upper triangular matrix by multiplying now by E3, 2. Now, what we've essentially shown then, by multiplying these three things together, we can view this as a single elementary matrix E. So we could multiply these three matrices first, and what I end up getting is EA is equal to U. It's what we had and what we saw in the previous lesson. Then applying these elementary matrices, barring a permutation, swapping of rows, we have this relationship. And what I want you to understand is that if I want to get A by itself, we need to be able to undo this matrix of E by using this concept of an inverse. By taking the inverse of E and doing left multiplication, we have this definition, that A is equal to the inverse of E times my upper triangular matrix U. And what we're going to find out is that by finding this inverse, once we have defined how we find the inverse, that inverse is actually going to be lower triangular. And finding this factorization is going to be really important because there's going to be information that we can gather from L and from U. But where that L comes from and why the elimination ideas use that lowercase l is they are connected to this matrix here through our elimination. And so in the next video, what we're going to ultimately do is try to define what an inverse matrix is and how we find it, as well as some of the important features. Not every matrix is invertible. We kind of discussed that earlier, that a matrix is only invertible if it's linearly independent, if it has full rank. So every column, every row is linearly independent. Its inverse would not exist if it is not full rank. We call that singular. And so what's fascinating, and we'll kind of prove this and talk about it, is that this matrix that we're dealing with in terms of E, by working with all of these, that the inverse does exist, that it is full rank, and that we can find it. So in the next lesson, the next video, what we will start getting into is defining that inverse, and then we will begin using those inverses to find L and define L. And you'll kind of see why when we talk about this inverse language in this first section, the added terminology of the L's, you'll see where these L's kind of pop back up, in particular with this example that we